Welcome back to Math 104. What is the probability that a randomly selected bottle is overfilled by between 0.75 and 1.75 milliliters? Let's first sketch the region. 0.75 milliliters lives right about there, and 1.75 milliliters up here. So that's 0.75 and 1.75 along the horizontal axis. And we are interested in the region between them. The most important thing to realize about this picture is that the region here in blue does not run from 0 to somewhere. It's a different kind of a region. So how do we handle it? 0.75 is part of the given information. We're going to have to look up 0.75 in the table and see what probability is there when z equals 0.75. We will also need to look up z equals 1.75. In fact, we've already looked up 1.75 in the table, and it corresponded to the probability 0.4599. Now, what does 0.4599 mean? Recall that it is the probability, which I'll now draw in red, that a randomly selected bottle is overfilled by something between 0 and 1.75 milliliters. A number that directly comes from a table always tells us the probability for a region that goes from 0 to somewhere, to that value of z. Now, if we look up 0.75 in the table, what will we find? We look in the 0.7 row and the 0.05 column. So 0.2734 is the probability that a bottle is between 0 and 0.75 milliliters overfilled. So 0.2734 is the probability associated just with this region here between 0 and 0.75. So what does that say about the probability that we're looking for of the blue region between 0.75 and 1.75? It must be everything from 0 to 1.75, which is 0.4599, minus the 0.2734 that we're subtracting off. Count everything from 0 to 1.75, and then throw away the part that we don't need. That difference is our answer, 0.1865. Given these two boundary points for our interval, it makes sense that we had to make two separate lookups in the table, but we had to think about what to do with the two numbers that came out of the table. Here we needed to subtract, but it's still a very good idea to draw the picture so that we know that subtracting is the right thing to do. Now let's look at the other example from the end of the last video. What is the probability that a randomly selected bottle is underfilled by at most 0.25 milliliters or overfilled by at most 0.4 milliliters? Let me draw 0.25 milliliters somewhere around there, and I label it by negative 0.25 to indicate that we are talking about underfilled bottles. Then my other boundary point will be at the 0.4 milliliter mark, somewhere around there. Underfilled by at most 0.25 milliliters, that means it's underfilled, but underfilled by not much. So we are shading between negative 0.25 and 0, and again between 0 and 0.4. So this is actually one region with a lower boundary that's below the mean, and an upper boundary that's above the mean. We will need to do two separate lookups in the table, but we'll have to think what to do with the probabilities that come out. We would like to look up z equals negative 0.25, but there don't seem to be negative numbers available as values of z within this table. But that's okay. What we're going to look up is z equals positive 0.25. When we do so, when we look in the 0.2 row and the 0.05 column, we obtain 0.0987. That number is the probability of a region that goes from 0 up to positive 0.25. But that should be the same probability as for a region that goes from 0 to negative 0.25, precisely because of the symmetry of the normal curve. The region from 0 to positive 0.25 is the mirror image of the region from 0 to negative 0.25. Therefore, they have the same probability. So the conclusion of our effort to look up z equals negative 0.25 in the table is this probability 0.0987. Thus we find that the region from 0 down to negative 0.25 has a probability of 0.0987. There's a 0.0987 probability that a bottle, a randomly selected bottle, will be underfilled by anywhere between 0 and 0.25 milliliters. We also have a region here from 0 to positive 0.4. We're going to need to look up 0.4 in the table, but when we do, we will need to add two probabilities. There are no subtractions required. In the previous example, we had to overcount something and then throw away the portion that we didn't want to keep. Here, there is no throwing away. The range of values we are interested in, the range of values that count towards our event, belong to two separate ranges, but each one is from 0 to somewhere. Therefore, the probability of each of these two separate ranges really is the result of a direct lookup in the table. So we've looked up negative 0.25, now we're going to look up positive 0.4, we'll get a probability for this piece, and then we can add. Looking up 0.40 in the table leads us to row 0.4 and column 0.00. The probability there equals 0.1554. We label 0.1554 in our picture, and now we add to find the overall probability of this event. This equals 0.2541. The probability is just over 1/4 that a randomly selected bottle has an error within this range. One more example before we move on. What is the probability that a randomly selected bottle is underfilled by any amount, or overfilled by at most 0.6 milliliters? Let's not be overwhelmed by the wording. Let's just go one phrase at a time. Underfilled by any amount, or overfilled by something. The word or means that we're going to have some region to the left of the mean, together with some region to the right of the mean. We are going to end up adding two probabilities. The shaded region to the left of the mean is actually everything to the left of the mean. Everything to the left of 0 is going to get shaded in here. That's the significance of underfilled by any amount. Then to the right of the mean, we're including all those bottles that are overfilled, but overfilled by not that much. Overfilled by at most 0.6 milliliters. Our region is going to end at 0.6 and shade in everything up to 0.6. Now, how do we think about the probabilities here? On the left side, we have a probability of 0.5. The region to the left of the mean covers half of all possible outcomes, so it contributes to 0.5 to the probability. We must add to that the probability that a bottle is overfilled by between 0 and 0.6, and that will be the result of a direct lookup in the table. When we look up z equals 0.60 in the table, we have the 0.6 row and the 0.00 column. That gives us a probability of 0.2257. 0.2257 here. The sum of these equals 0.7257, and that is our answer. That is the probability that a randomly selected bottle is underfilled by any amount or overfilled by at most 0.6 milliliters. Now let's come back to test scores. In 2013, the mean math SAT score was 514 with a standard deviation of 118. I'm not making it up, this comes from the College Board. We would like to answer such questions as, what is the probability that a randomly selected student scores between 514, that's exactly the mean, and 600? Now that is not a whole number of standard deviations away from the mean. We're going to need to adapt what we just did with the standard normal to this example where the mean is not 0 and the standard deviation is not 1. But we're still going to need to look up values in that table. We'll also want to ask what percentage of students score above 620, and something of a new kind of a question, to be in the top 20%, what score would a student need to receive? We have not yet addressed a question like this one. The key idea here is that of a z-score. The z-score of a data point equals the number of standard deviations it is above the mean. This number can be negative, in which case the z-score indicates how many standard deviations below the mean the data point lies. Our definition of z-score is that the z-score of a data point is computed as raw score minus the mean divided by the standard deviation. We've actually done this already in an earlier example. For example, test score minus the class average divided by the standard deviation. This numerator, test score minus the average, tells you how many points above the mean the student scored. To convert from points to standard deviations, we need to know how many times sigma goes into that number of points. We have to divide by sigma. Using this idea of z-score, let's take another look at the SAT scores, whose mean was 514 and whose standard deviation was 118. What is the probability that a randomly selected student scores between 514 and 600? This point in the middle right here, that is the mean. And the mean is 514. The z-score for 514 is computed as score minus the mean divided by the standard deviation. That's just a fancy way of saying 0 over 118, which is 0. Thus, a student who receives 514 points has a z-score of 0. That's just another way of saying that that student scored right at the mean. How about 600? That's going to be slightly under one standard deviation above the mean. To find the z-score there, we compute 600 minus 514. It's always score minus the mean, all divided by the standard deviation. So we must compute 86 divided by 118, which is approximately 0.73. We only need 2 decimal places of accuracy because our table can only tell one z-score from another based on 2 decimal places of accuracy. So someone whose SAT score is 600 has a z-score of 0.73. Such a student scores 0.73 standard deviations above the mean. The region in question is just the region between 514 and 600, or between z equals 0 and z equals 0.73. The significance of shifting from SAT points to z-scores is that now we've turned our normal curve with a certain mean and standard deviation into the standard normal. We're getting to be great experts at this. We look in the 0.7 row and the 0.03 column, and we find 0.2673. The probability we're looking for equals 0.2673. Before going on to the next video, answer the following questions about the same SAT situation with mu equals 514 and sigma equals 118. What percentage of students score above 620? So think what the region looks like, and think what you have to do to 620 before you look anything up in the table. And then, what is the probability that a randomly selected student scores between 450 and 550? I recommend drawing the picture both times.